We have discussed in my last lecture the Maxwell's speed distribution formula, and this speed distribution formula could be transformed into any distribution of any property which is directly linked with this speed of the molecules. Say you can have a momentum distribution, or more important, kinetic energy distribution, by replacing c, speed, corresponding to the momentum or kinetic energy. Let me first transform the, let me first write the Maxwell's speed distribution formula. Maxwell's speed distribution of molecules, of course in the gaseous state it is dNc by n equal to 4 pi and m by 2 pi kt to the power 3 by 2 and e to the power minus mc square by twice kt and c square dc. And this is already I have told, this is the fraction of the molecules having the speed c within the range dc and m the molecular mass of this gas and t the temperature. So actually it is also called the probability of a molecule to have the speed c within the small range dc of this gas having the molecular mass m and the temperature T. And if we like to transform this speed distribution into momentum distribution, then P the momentum equal to mc, or use from this you can write a dp or c equal to p by m, or dc equal to dp by m. This P is the momentum of this molecule. So if you put here, as you can replace c square dc and here also c square, then you can have the momentum distribution formula. And the momentum distribution formula, you can do it at home. This one equal to 4 pi and it is 1 by twice pi m kt to the power 3 by 2 and e to the power minus and e to the power minus p square divided by twice m kt and p square and dt. You can do it by yourself and just tally whether your result is coming with this value. But more important in chemistry is the kinetic energy distribution of molecules. And this kinetic energy distribution, of course, I have also shown that it is C and it is FC. It is origin and this curve is like that. Already shown earlier. The kinetic energy of a molecule is directly linked, is related with epsilon equal to half mc square. Epsilon is the kinetic energy of this molecule, m the molecular mass and c the speed. So kinetic energy distribution we can easily get by replacing this c in terms of this epsilon. So from c square, from this c square equal to twice epsilon by m, twice epsilon by m, or c equal to root over of 2 by m and epsilon to the power half. So dc equal to root over of 2 by m into, it is half, and epsilon to the power minus half and d epsilon. This is equal to 2 and 2. So it is 1 by 1 by root over of 2 m epsilon and d epsilon. 2 cancels, here 2 and here root over 2, so root over 2 coming here and m and this is also epsilon. So you now replace this c from the speed distribution of the molecules in terms of this epsilon. So in this case, this dn epsilon by n, it is the fraction of the molecules having the kinetic energy epsilon with the small range d epsilon and t the temperature. Let us see what will be the formula is coming up. So this is 4 pi and m by twice pi kt to the power 3 by 2 and e to the power here epsilon equal to half mc square, half mc square, so minus epsilon by kt, and instead of c square we can write twice epsilon by m, and instead of dc we can write into 1 by root over of twice m epsilon and it is d epsilon. So if we simplify this one, then m to the power half and m to the power 3 by 2, so m and m, all the m will be cancelled, and again this 2 and root over 2, then root over 2 here, root over 2 and here root over 3 by 2, so it could be written as 2 and here pi and pi to the power 3 by 2, so root over pi and e to the power minus epsilon by kt, and this one 2 cancels, 2 cancels, 2 cancels, and here 1 by kt to the power 3 by 2 and e to the power minus epsilon by kt, and here it will be root over of epsilon and d epsilon. So the kinetic energy distribution is that d and epsilon we can write here. D n epsilon by n equal to 2 by root over of phi, and here 1 by kt, and to the power 3 by 2, and e to the power minus epsilon by kt, and root over epsilon and d epsilon. So 2 by root over pi, 1 by kt to the power 3 by 2, it is power minus epsilon by kt and root over epsilon d epsilon. So one thing you must notice, very striking feature of this kinetic energy distribution does not contain the molecular mass. It means that the kinetic energy distribution does not depend on the nature of this gas. It only depends on the temperature. It only depends on the temperature. And for that reason, you can see very light gas, say hydrogen, and here say uranium hexafluoride, very heavy gas. In this case also, this is about this is about this is about 349 molecular weight. Here it is 2. So in spite of this molecular mass of these two gases at a given temperature, both the gases will give you the same kinetic energy distribution. This is the beauty of this kinetic energy distribution formula. If we draw this curve here, or you can write this F epsilon into D epsilon, and this F epsilon you can call the kinetic energy distribution function, and this is equal to 2 by root over of phi, and here 1 by kt to the power 3 by 2, and e to the power minus epsilon by kt, and kt and root over epsilon and d epsilon. So there is a notable difference between these two distribution functions. Here it is c square, here epsilon, here root over epsilon. Epsilon is a very small quantity. For a molecule, it is a fraction. So since it is fraction, so epsilon root over is having greater value than this epsilon. And for all sorts of fractional terms, the root over is having this higher value than the original one. Say it is so in this case, if we draw this diagram, here the epsilon, here origin, and here F epsilon, what will be the curve automatically whenever the epsilon 0, this FC F epsilon also equal to 0. So this curve will start from origin. And this curve will start from origin. And then since epsilon root over epsilon is greater than epsilon, so this with the increase of epsilon, this value will increase and this exponential term will decrease. It is like this Gaussian distribution function. So Gaussian distribution function, in this case, one term, this non-exponential term will increase this value of f epsilon, while this exponential term will try to decrease this value of f epsilon. But since here c square, here epsilon, here root over epsilon is greater, so it will increase very sharply and attains maximum when the epsilon is having the higher value. This exponential term will dominate and this curve will fall. This curve will fall very slowly and becomes asymptotic. That means this curve will meet with this epsilon axis at infinite value. So in a finite value of epsilon, these two curves, this curve and this axis will run parallel. So this is you can see the difference. This you can see the difference between this speed distribution curve and kinetic energy distribution curve. And from this relation, I have already told you that this distribution of a property will help to calculate the average value of that property. So here also we can take this average value of this kinetic energy, and this one according to this formula here 0 to infinity and here epsilon and dn epsilon by a. This is the probability of a molecule to have this kinetic energy, molecular kinetic energy epsilon, and epsilon will range from 0 to infinity. If you replace this dn epsilon by n here, then it is 2 by root over pi constant 1 by kt to the power 3 by 2 and integration 0 to infinity, and here it is here epsilon to the power half and here epsilon, so epsilon to the power 3 by 2 and e to the power minus epsilon by kt and d epsilon. So this sort of integration you can easily calculate by the use of this gamma function. A gamma function, probably you can remind this 0 to infinity x to the power n and e to the power minus ax and dx, and this will give you this gamma n plus 1 and divided by a to the power n plus 1. Here n equal to 3 by 2. So this average expressions of this average value 2 by root over pi and 1 by kt to the power 3 by 2, and this integral value n equal to 3 by 2, so gamma 5 by 2, and here 1 by kt is a, and this is also 5 by 2. So you can also write a 2 by root over pi and 1 by kt to the power 3 by 2 and into here 3 by 2 and half and gamma half and here kt to the power 5 by 2. 5 by 2. If you simplify this one, then 2 by root over pi and here 1 by kt to the power 3 by 2 and 3 by 2 and here 2 and 2 cancels, so 3 by 2 and this value is root over of pi and this kt to the power 5 by 2. kt to the power 5 by 2. So this root over pi and root over pi cancels, and it is 1, 2 cancels, 1 by root over pi, 1 by kt and 3 by 2, and this will give you epsilon bar equal to 1 by kt to the power 3 by 2, here kt to the power 5 by 2, so it is 3 by 2 and kt. 3 by 2 kt. So the average kinetic energy is equal to 3 by 2 kt, or you can write epsilon bar equal to 3 by 2 RT. R is the molar gas constant. So naturally you can do problems. If you like so, then you can solve this problem. From this one, say calculate percent of molecules in a gas having kinetic energy 4000 joule mole inverse to 4100 joule mole inverse at 300 Kelvin. So you can put here, it will give you the fraction, and when fraction is multiplied by 100, it will give you the percentage. So if you put here, let me write this one, dn epsilon by n equal to here 2 by root over of 3.14, and here you can write also in terms of this molar gas constant. So this is equal to 2 by root over of pi and 1 by RT to the power 3 by 2 e to the power minus E by RT and root over of E and dE. D. This whenever K is replaced by R, this unit will remain the same. There will be no change. So here 1 by 8.31 joule mole inverse Kelvin inverse into 300 Kelvin to the power 3 by 2 and into e to the power minus 4000 joule mole inverse and divided by 8.31 joule mole inverse Kelvin inverse into 300 Kelvin, and here it is root over of into 4000 joule mole inverse, and d epsilon is 100 joule mole inverse. So naturally here joule mole inverse to the power 3 by 2, here joule mole inverse to the power half, and here joule mole inverse to the power 1. So this one, and this value cancels. This is also cancelled. Here also this is cancelled, K inverse, K inverse. So only the numerical values are there. If you use the calculator, then it will give you 0.011 0.0115, or in terms of the percentage 1.15%. Means if you have 1000 molecules in your gas assembly, then the 115 molecules will have this kinetic energy 4000 joule mole inverse to 4001 joule mole inverse. If you have the 10,000 molecules, then you have 115 molecules. I have this sort of energy at 300 Kelvin. Now also one problem I can give you, this epsilon bar equal to 3 by 2 kT or E bar average molar kinetic energy is equal to 3 by 2 RT. So here also you can calculate the average kinetic energy, average molar kinetic energy of molecules at 300 Kelvin, and you do it by yourself, and answer will be 3739.5 joule mole inverse. Now I am coming to a very important formula. The fraction of the molecules kinetic energy greater than or equal to say 4000 joule mole inverse at 300 Kelvin. This is a very important. Now let me first formulate. You can say this is suppose this epsilon 1. The molecules having the kinetic energy greater than or equal to epsilon 1, you can get it from this area. Area of right hand side of the coordinate drawn at epsilon 1. And this area equal to n epsilon 1 by n, or fraction of the molecules having the kinetic energy greater than or equal to epsilon 1, that you can have it from this curve, if you can draw this curve. But I like to formulate this one from this relation. Say fraction of molecules having kinetic energy greater than or equal to epsilon 1. Greater than or equal to epsilon 1 at equal to 1. So you can formulate here, say n epsilon 1 divided by n equal to integration, lower limit is epsilon 1, greater higher limit is infinity, and dn epsilon by n, and this is equal to 2 by root over pi, and here 1 by kt to the power 3 by 2, and here the integration epsilon 1 to infinity, and e to the power minus epsilon by kt, and root over of epsilon and d epsilon. Let us solve. This integration you could not solve by use of gamma function, as here the limit is not 0 but epsilon 1. So this, let us put this epsilon equal to kt temperature and x square. So d epsilon equal to kt and d x square, and also the limit will be changed as x equal to, whenever epsilon is changing by this x, in terms of this x, it will be root over of epsilon 1 by k. So root over epsilon and root over epsilon is equal to root over of kt and simply x. Now we put here this integration is a little bit complicated, and so this n epsilon 1 by n, it is the fraction of the molecules having the kinetic energy greater than or equal to epsilon 1. at a given temperature. So this one equal to 2 by root over pi, and here 1 by kT to the power 3 by 2, and this integration limit is changed, root over of epsilon 1 by kT, and here it is infinity, remains the same, and e to the power minus, instead of epsilon you can write this one, so kT cancels, so it is simply the x square, and root over epsilon equal to root over of kT into x, and this d epsilon equal to again kT and the x square, So if we simplify this one, then this will give you 2 by root over pi and 1 by kT to the power 3 by 2, and you can write this one and also kT and root over kT, then kT to the power 3 by 2, and it is minus integration root over of epsilon 1 by kT and infinity, and instead of writing dx square and e to the power minus x square, we can write this x into d and e to the power minus x square, e to the power minus x square, bracket goes. If we do this from here to here, then it is our minus x square, your minus x square, and also the dx square. Now another step, then this one and this one will cancel. So 2 by root over of 5 and here minus, and integration, it is the product of the two variables, and first this x remains the same, and its integration is e to the power minus x square, and the limit is root over of epsilon 1 by kT, and this is infinity, and minus integration root over of epsilon 1 by kT, and here infinity, and differentiation of the first variable, so it is 1, and here this integration, this one e to the power minus x square and dx, third bracket close. But x equal to kT x square, epsilon equal to kT x square. So x square equal to epsilon by kT. Epsilon is very small in comparison to kT. So x square is large. So e to the power minus x square is very small. And also you can neglect this very small e to the power minus x square. So this integration you can ignore. So this one equal to 2 by root over of pi and if you omit this minus, then x e to the power minus x square, and here infinity, and here root over of epsilon 1 by kt. Okay. So when you are putting this limit, then 2 by root over pi, and in this case into root over of epsilon 1 by kt, this value, and e to the power minus epsilon 1 by kt, and whenever you are putting this infinity, e to the power minus infinity means it is 0. E to the power minus infinity equal to 0. So this term, this whenever you are putting this second, this lower limit, this term becomes 0, as x e to the power minus x square, e to the power minus x square will be getting 0 much before, then x becomes infinity. So this is the formula n epsilon 1 by a. You can write here we can write here 2 by root over pi, root over epsilon 1 by kt, and e to the power minus epsilon by kt. So you can write also this 2 by root over pi, and here if you consider this molar kinetic energy, then it will be E1 divided by RT, and e to the power minus E1 by RT. R is the molar gas constant, E is the kinetic energy per mole. So it is the fraction of the molecules having the molar kinetic energy greater than or equal to epsilon 1 at a temperature T. If you draw this curve, how the temperature affects this value, effect of temperature on this fraction, then this value here it is epsilon 1, here it is 0, and n epsilon 1 by n. So when epsilon 1 equal to 0, actually you can write also root over 2 by pi into root over of epsilon 1 by kt, and e to the power minus epsilon 1 by kt. So epsilon 1 is plotted, n epsilon 1 is plotted against epsilon. Then here, this is the non-exponential term, this is the exponential term, and the effect of t here also there, here also there. But it will start from epsilon 1, when epsilon 1 equal to 0, then this one equal to 1. So this curve will start 1.0, and at lower temperature, this term, whenever temperature is low, this is high, and this is dropping down, and this one is also, temperature is low, this is high. But the exponential term will dominate over the non-exponential term, so it will rise more rapidly, it will decrease, it will drop from, suppose this is 200 Kelvin. If you increase this temperature, then this term again becomes less, and this will give you the 400 Kelvin, and again this one is 600 Kelvin. So everything, as the temperature is increased, say temperature is increased for a particular value of epsilon 1 dash, this fraction increases very remarkably with the rising temperature. And whenever the temperature becomes infinity, very large, then it will be like this one, and all the molecules will have the uniform kinetic energy, no distribution. So these are the two terms. One is non-exponential, other is exponential. With at lower temperature, this is high, and this one is dropping down more rapidly. And when the temperature is increased, this one will not decrease so rapidly, and so this curve we can obtain. You can also calculate the percent of molecules in a gas having kinetic energy greater than or equal to 4000 joule mole inverse at 300 Kelvin. You can put here. So this the n epsilon n E1 by n, this is the molar kinetic energy. This is equal to 2 by, here you can write this root over of 3.14, and here it is root over of 400, 4000 joule mole inverse, and divided by RT 8.31 joule mole inverse Kelvin inverse into 300 Kelvin, and e to the power minus this one again 4000 joule mole inverse, and divided by this R 8.31 joule mole inverse Kelvin inverse into 300 Kelvin. So Kelvin inverse Kelvin cancels, joule mole inverse cancel, and here also joule mole inverse Kelvin inverse all cancels. And if you do this problem, if you calculate this problem, it will give you the value 0.1622. Or 16.22%. Means if you have the 10,000 molecules, then only 1622 molecules will have the kinetic energy greater than or equal to 4000 joule mole inverse. This is 10,000. So here also this one. If you consider 10,000, if you consider the 10,000 molecules, then out of these 10,000 molecules, you have 1600 two molecules will have this sort of energy. So this is the case. So far we have discussed very elaborately the kinetic energy distribution, and from this the average kinetic energy of a molecule. And the next one, very important, the fraction of the molecules are having the kinetic energy greater than or equal to a certain value epsilon 1. You know, in chemical kinetics, the molecules are colliding, and all the collisions are not effective for this reaction. Only those molecules that can acquire the minimum energy, which we call the activation energy, these molecules only will react. So naturally, in that case, it becomes necessary to calculate the fraction of the molecules having the kinetic energy greater than or equal to this activation energy. So this is all about my lecture, today's video lecture, and in my next class I shall try to elaborately discuss the Maxwell's distribution law in 1 dimension, in 2 dimensions, and show you the possible criteria. Thank you all who are watching this video.